Okay, so today we're just going to jump straight into it. It is the Friday before your spring break, so we're not going to do a problem of the day or anything like that. If you watched the last video, you'll know that we just had one example left to get through to finish this section of notes. That's what we'll do today, and we'll end off our progress on momentum, work, and energy before spring break at conservation of momentum in 2 dimensions. That means that we have to do work, kinetic energy, gravitational potential energy, the law of conservation of energy, and springs next. So we'll do that after spring break. But for the time being, we are just going to finish the conservation of energy in 2 dimension problem. So, problems. All right, so here we are. We've got an example where we have a 2,000 kilogram car traveling east at 24 meters per second, enters an icy intersection and collides with a 3,600 kilogram truck traveling south at 10 meters per second. If these two lock together, so that's important, we've got locking going on, which means that we are going to have an inelastic collision, okay, where they are going to stick together. If we have this, then that means that in the final part of our problem, we have the two objects kind of becoming one in a way, right? We have them becoming one, which means that we're going to draw them together and their masses are going to combine. So let's set this up. We'll draw out the scenario. I'll use 2 different colors again for the 2 different cars so we can just see it a little bit better visually. So we've got before and we've got after. Where use here? Okay, before and after. Okay, let's say for the sake of how, okay, let's take a look at how these cars are going to collide for the car and the truck. So you've got a 2,000 kilogram car traveling east at 24 meters per second. I'm going to draw this from like an above kind of perspective. So there's our car. We'll call it C. Okay, that'll be its subscript. So we've got the car traveling east like that. And then I'm going a little bit slower, but it's a bit heavier, so I'll draw it a bit bigger. There's the truck, but it's moving a little bit slower. And it's going south. So what we can see here is that we're going to have a scenario where they're going to collide and they're both going to shoot off going in this direction down like this. Now, because that's going to be my resultant direction of motion, when I set up my positives and negatives here, I'm actually going to make, contrary to what we normally do, I'm going to make east and south positive, and I'm going to make north and west negative. Okay, and that's because we see that it's going to be moving southeast after this collision. So they collide, and you've got the car right here, and maybe collision happened at the front there. So then we've got the truck right here, and they are stuck together as one total mass. Oh, the truck got bigger. That's okay. So you get the idea. They are stuck together and are now moving in a direction like so. Something like that. Okay. I'm going to call this VBF. Now, obviously, we know what the F means. The F means the final. Okay. B is my subscript, which stands for both of them together. Okay, so that's what I'm going to use. Now, here's the thing, is that both means that we're treating the entirety of these two together as one mass, okay? And what that means is that we're going to have an angled final velocity, right? So we're going to have some sort of angle happening here. Now, what that also means is that there's going to be an x component and a y component. right? And we're going to need to find the x and y components. We don't know the angle. We don't know the final velocity. That's what we're trying to find, right? We're trying to find what is their velocity after impact. Okay, so we're going to have to break this up into its x and y components. We're going to have to find the x. We're going to have to find the y. And then we're going to have to combine them at the end to find the hypotenuse and the angle. So that's how we're going to do this. Let's start off with the y direction, just because I feel like it, okay? So we'll start off with the y. The y direction follows the same principle that everything else has in this scenario. We have a conservation of momentum. So that means that the momentum initially in the y direction is going to be equal to the momentum in the final y direction. So PIY equals PFY. What that means then is that I've got the momentum of my car in the y direction initially, and I've got the momentum of my truck in the y direction initially is equal to the momentum of the two of them after in the y direction. So this right we're going to call VBFY, and this right here is VBFX. Okay, and what that means is that my car has an initial VCIX, and a VCIY, whereas my truck has a VTIX and a VTIY. Okay, now let's take a look at which of these are going to be zero. The car is not moving at all in the y direction initially, so that's zero. And the truck is not moving at all in the x direction initially, so that's going to be zero. So they both only have x and y components respectively, okay? So the car is only moving in the x direction, the truck is only moving in the y direction. So when I go about adding up this is my total momentum. So I've got the momentum of the car, which is the mass of the car multiplied by the velocity of the car initially in the y direction, plus the mass of the truck multiplied by the velocity of the truck initially in the y direction is going to be equal to the mass of both of them multiplied by the velocity of both of them finally in the y direction. Okay, so those are all coming from here, here, and here. So like we have there, this entire one is just going to be equal to zero because the velocity of the car in the y direction was just zero. It wasn't moving up and down or up or down at all. Okay. And then what that means is that I can plug in my mass of the truck, which it says in the question is 3,600. So 3,600 times the velocity of the truck in the y direction, which was 10, and set that equal to the mass of both. So the mass of both, let's use a different color here to just show how we get the mass of both. We just have to add up the mass of the truck and the mass of the car. So this is just 2,000 plus 3,600. Okay, and that is 5,600. So 5,600 multiplied by, well, that's what we're trying to find. We're trying to find the y component of the final velocity of both of them together. Okay, if we do that, if we solve for VBFY, we will get 36,000, right? 3,600 times 10 is 36,000 divided by 5,600, which will give us 6.43 meters per second. And we know that it's south. Okay, so we're not technically looking for a vector here, but we can give it, just to be clear, it is south. Okay, so we've done the y. Let's focus on the x component now. So the x component has the exact same initial setup. The initial momentum in the x direction is equal to the final momentum in the x direction. Conservation momentum always means that that's going to be the case. So we have the mass of the car multiplied by the velocity of the car initially in the x direction, plus the mass of the truck multiplied by the velocity of the truck initially in the x direction is equal to the mass of both multiplied by the velocity of both finally in the x direction. That's an F. Okay, so there we go. Now there's one key thing here. The velocity of the truck initially in the x direction was 0. It wasn't moving at all in the x direction. It was only moving in the y. So this becomes 0. Makes our life a lot easier. You can see that we actually would be able to do these problems with both of these being on angles initially. You'd have to separate these into their x and y components, and then separate this into its x and y components and solve. It would just make for one extra step. You wouldn't have zeros here. You would have an x component of both of them and a y component of both of them. So it would make it a little bit more of a complicated problem, but only in the sense that it would just be a more complicated vector addition, which we've all done before, so we should know how to do them. So the mass of the car is 2,000 times the velocity of the car initially in the x direction, which the question tells us is 24 meters per second. That is 0, and then we've already calculated MB. MB is 5,600. 5,600. So 5,600 times VBFX. So let's solve for the final velocity of both of the cars in the x direction. If I multiply 2,000 by 24, I get 48,000. So 48,000 divided by 5,600 should give me VBFX. I'll do the vector because I'm going to give a direction here. And you'll get 8.57 meters per second east. Again, knowing it's east just because of how I set it up. So now what I have is I have both the x and the y components of these two. So what I've basically made here is I've made another triangle. I've made a triangle like this, where we've got 8.57 and then south of 6.43. So our job now is to find the hypotenuse, which is VBF, and the angle, because the question does ask what is the velocity, right? If you look back up at the question, it says what is the velocity? Therefore, it is important to find not only the speed, but also the direction. So there we go. We've done great so far. We've got one final step. We've done this step a whole bunch of times in a bunch of other units. We need to find VBF, which we use Pythagorean theorem. So a squared plus b squared equals c squared. So we have the square root of 8.57 squared. That's our a. And then our b can be 6.43 squared. Take the square root of that, and that should give you 10.7 meters per second. And then let's find theta. In theta, we use the inverse tangent of the opposite over the adjacent. The opposite is 6.43, and the adjacent is 8.57. And if you do that, that should give you 36.9 degrees. So writing it all together, VBF in final, in the end, is, we notice that going based on, so I'm going to write it out, it's 10.7 meters per second, east, 36.9 degrees south. So that's our final answer. Now, sig figs wise, not very ideal for this problem because in the question, we do only have one sig fig for some of these. So your answer would end up just being, I guess, you could say just 10. I don't really like it. I'm going to say here, whoever designed this question did not take into account sig figs because it changes your answer too much. So that is it for conservation of momentum in 2 dimensions. There are some tricky problems in there. I've had a few of you email me asking questions about some of them, and that's awesome. Keep up those emails. I will respond to them as I can. You've got spring break coming up now, so I would just take this time to relax, take care of yourselves, and if you're looking for something to do, you could give it a shot. Some of these questions, it would be great to come back and all be kind of at least the same point. So being here and ready to move forward, that would be ideal. Please stay in contact. If you have any questions, like I said, you can just email me and we'll get back to our regular classes in, I guess, 10 days. What is it going to be? Roughly 9 days, 10 days time. Enjoy your break. We'll see you then.